So we would be discussing four types of geometry. Okay, and I told you the types of ligand in the last class. Monodentate ligand, bidentate ligand. Bidentate ligands are capable to make two bonds with the transition metal. And then we discussed uh, polydentate ligand, that was EDTA, is a hexadentate ligand. Hexa means it can donate six electron pairs, and it can make six dative bonds with the metal. So then we have geometry, or you can say the structure of complexes. Number one, we have linear shape, linear structure. So how can you determine that the structure is linear? Of course, if the coordination number is 2. And I told you, what do you mean by the term coordination number? Coordination number means the number of dative bonds between the metal and a ligand, where the bond angle is 180 degree. It doesn't matter what type of ligand you have, but it should be monodentate ligand, of course. Okay. So coordination number is 2, and the coordination number must be 2. So then I can say that the shape is linear and the bond angle would be 180 degrees. Okay. Then when we have octahedral complex, so octa means when the coordination number is 6. Octa means when the coordination number is 6. It may be just like that, or it may be like that. You can see 3 over there, but of course this is a bidentate ligand, means that one bidentate ligand is going to have two dative bonds. So if you have in total 3 bidentate ligands, so how many dative bonds it would be forming? So 6. That's why the coordination number is 6 in this case. You can see 1, 2, 3, 4, 5, 6, 6 dative bonds. 1, 2, 3, 4, 5, 6, 6 dative bonds. Both ligands are going to make 6 dative bonds. That's why I can say the geometry of both ligand is octahedral. Okay. Then then we have tetrahedral. Then we have tetrahedral. Okay. So
So what's the angle for octahedral?
sorry.
Angle for octahedral.
Oh, okay. Angle for octahedral. It is 90 degree. 90. 90. Then 90. And then this and this 180 degree. Okay. So bond angles are 90 degrees and 180 degrees. Well, by the way, he would specify like to which he is going to ask. Like I'm talking about the bond angle. So then you can say it's 90 degrees. Okay.
Okay.
Then we have tetrahedral geometry. Tetrahedral is very famous term, of course, when we like think tetrahedrals, of course. CH4 comes to our mind. CH4, methane. It's also a tetrahedral. But of course, we are discussing transition metals, so we have to discuss the transition metals. So both for both, whether it is tetrahedral, whether it is square planar, so both coordination number is 4. So whenever you can see the coordination number is 4, it may be tetrahedral and it may be square planar. How can we decide whether we would be having tetrahedral or square planar? So remember, if you can see chlorine and the charge is 2 minus, whether you have copper, whether you have cobalt. This is very important point. If you can see chlorine as a ligand, overall charge is -2, and this is copper, or sometime it may be cobalt. It would be tetrahedral. It would be tetrahedral. And you know the geometry, like the bond angle for the tetrahedral is equal to 109.5 degrees. Means that they are far away from each other. You know, it depends on multiple factors. Like how can we decide whether the geometry would be square planar or tetrahedral? So you are not supposed to like think about that. It's a long story. That wouldn't be the part of syllabus as well. You must know only to like you are supposed to only identify the compounds, and then you are supposed to decide that which geometry this complex is going to have. So copper or cobalt, ligands are chlorine, and the charge is 2 minus, like the negative charge. So then the geometry would be tetrahedral and the bond angle would be 109.5 degrees. And if you can see platinum, if you can see platinum, so platinum would be giving you a square planar complex. And for the square planar, the bond angle would be 90 degrees. This is called cisplatin. This is called cisplatin. We would be using the term cis and trans later on when we would be discussing the isomerism. This is called cisplatin. Like I have written the four chlorine atoms. It may it may be NH3 and NH3 rather than the four chlorine. It may be NH3 and NH3. If you can see this, so you can say this is called cisplatin. Cisplatin is used as an anti-cancer drug. So you know what it does? It would be binding to DNA. It would be binding to DNA in cancer cells. So of course, it would be preventing the replication of DNA, of course, and cell division. That's why it is used as an anti-cancer drug. He would be asking it. They have mentioned in your specification. According to your specification, you have to know about the cisplatin drug. So what it does? So it is used as an anti-cancer drug. So what is the function of that drug? Of course, it would bind to DNA in cancer cells and it would prevent the replication of DNA, the replication of DNA strands. And of course, it would be preventing the cell division. Abnormal division is called, the cancer. So when it would be binding to the DNA, so of course it would be controlling the cell division. So that's why it can act as an anti-cancer drug. So what I told you, I'm going to summarize it. If you can see copper and cobalt with the chlorine, charge is 2 minus, so it would be tetrahedral. And if you can see platinum, whether you have 4 chlorine, whether you have 2 chlorine and 2 NH3, whether you have 2 chlorine and 2 NH3, so then you can say it is a square planar and the coordination number is 4 and the bond angle is 90 degrees. Simple. So you can see this, it's copper, of course. So you would be writing directly it's tetrahedral. Copper, chlorine with the charge 2 minus. Okay. So this is called tetrahedral complex and the bond angle would be 109.5 degrees. Simple, very simple. Okay. Then we have, after discussing the geometries, geometry is very important part. Geometry is very important part of this. So after discussing this, we have two types of isomerism that we would be discussing in this. Stereoisomerism. What we would be discussing is stereoisomerism. There are two types of stereoisomerism. Number one, we have optical isomer. Number two, we have cis-trans isomer. Optical isomer and then cis-trans isomer. Cis-trans isomer is also known as geometrical isomerism. So let's start with geometrical isomerism. So uh, cis means the same side. Trans means opposite side. How can we decide? You can see the bond angle. Okay, you can see the bond angle. If the two ligands are attached with an angle of 90 degrees, so you can say this is cis. And if the two isomers are attached with an angle of 180 degrees, so you can say they are trans isomer. Like if you can see this, um, okay. Let's see another example. Yeah, see this. So the two the two same ligands are attached. The two same ligands are attached, okay, with an angle of 90 degrees or like this, like this. So this is called cis. This is called cis. I'm supposed to write this NH3 over there. I'm supposed to write this NH3 over there. So this is NH3. This is what? This is NH3. And this is your chlorine. This is your chlorine. Okay. So it's 90 degrees. The same side, it's cis. Opposite side, angle is 180 degrees. It's trans. This is the very important drug that I was telling you. It is anti-cancer drug. Okay. It's like this is called like the cis and trans isomerism. You would see the cis trans isomer. You would see the cis trans isomer in octahedral as well. In octahedral as well. Remember, in octahedral as well. How you will see? How you will see in octahedral complexes? You can see that 90 degree, 180 degrees, it's trans. 90 degrees, it's cis. Of course, it's an octahedral complex. Okay, it's an octahedral complex. So, but remember, you can't see cis-trans isomer in tetrahedral complex. This is important point. You can't see cis-trans isomer in tetrahedral complex. You know why? You know why? Because in tetrahedral, what's the bond angle? You will see, sir, 109.5 degrees. So how is that possible that you would be having bond angle 90 degrees or 180 degrees? No, of course, the answer is a big no. Because in tetrahedral complexes, we can only have the bond angle that is equal to 109.5 degrees. That's the main point. Okay. So this is called cis and trans isomerism. Now we have optical isomerism. Now we have optical isomerism. Optical means when you have non-superimposable images. If you remember when we were discussing this in organic chemistry, so we used to learn about the chiral carbon, like the carbon which is going to attach with four different groups, but that is different and this is different. So optical means when you have non-superimposable mirror images. What do you mean by non-superimposable mirror images? If you can see, this is my hand, this is my left hand, this is my right hand. So the mirror image of this left hand would be the right hand. And if you are going to superimpose it, if you are going to superimpose it, so they cannot be superimposed, just like that. So the flasks can be superimposed 100%. So this is not optical isomer. This would be giving you optical isomerism. That's the key point. That's the key point. So how will we know that whether we are going to have non-superimposable images or superimposable images? The structure would decide. The structure would decide. Remember. So let's suppose, uh, let's suppose. Mhm, yeah, see this. So what is the mirror image of this? Listen very carefully. What is the mirror image of this? This. I'm writing down the mirror image. See this. This is the mirror. This is the mirror. And this is the mirror image of this. This is the mirror image. Yes or no? Yes or no? Am I right?
Um,
So,
yeah,
yeah.
you just flipped the.
Of course, I have flipped, but the thing is that the ligands are same. I have flipped. I did left, right, and right to the left. But but the thing is that the ligands are same. We are not feeling that we have flipped, but right, but in fact we have flipped this. So let's do This, I'm going to superimpose it. Yeah, it's going to superimpose 100%. So optical isomer is not possible. Optical isomer is not possible. The mirror image should not be superimposed. The mirror image should not be superimposed. Okay. So let's suppose I'm going to make I'm going to make the mirror image of this. I'm going to make the mirror image of this. So that would be that would be just like that. Left becomes right and right becomes left. So this is the mirror image. So I'm going to superimpose it. Oh, it's not going to superimpose. So yeah, this is known as the optical isomer of this compound. Simple. Are you getting my point?
Yeah.
Yeah. So you have to see over there, okay, like what would be the mirror image? And is the mirror image superimposable on another isomer? So if yes, so optical isomer is not possible. And if not, then optical isomer is possible. What about octahedral complexes? What about the octahedral complexes? If you can see for the trans one, I'm going to draw the mirror image of this just like that. This is the mirror image that I'm going to draw. Okay. So of course, this is the mirror image and I'm going to superimpose it. Of course, it would be superimposed. The ligands are same. So optical isomer is not possible for the trans. What about the cis? Right becomes left, left becomes right. When you're going to superimpose it, it would not be superimposable on each other. Am I right? So then I can say optical is possible for the cis, but optical is not possible for the trans. Are you getting my point?
Yes.
Yeah. So this is all about the isomerism in complexes. It's very easy. Okay, then color of complexes. This is important point, important topic. Complexes of transition metals, they are going to form colored complexes. And I told you the d orbitals, like degenerate orbitals, they all have the same energy. Let me tell you again that, yeah, see this? They are called d orbitals. They are called d orbitals. Okay. So dxy, dyz, dzx, dx square, y square, and dz squared. They are called d orbitals. And they are having the same energy. That's why I can say we can use the term degenerate, means that they all have the same energy level. Then what would happen? Then what would happen? So you can see this. Let's suppose y copper 2 plus is blue. Let's suppose y copper 2 plus is blue. So configuration for copper 2 plus is this. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. 4s1 and 3d10. So copper plus 2 means that it has to remove 2 electrons. Okay. After the removal of 2 electrons, it becomes 3d9 and 4s0, just like that. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. This is these are the d orbitals. These are 5d orbitals. These are these are 5d orbitals. Okay. So now they are at the same energy level. Nothing happened so far. So they are called degenerate orbitals. Okay. I'm talking about I'm talking about the this complex. Okay. Where the water is going to make a bond with this copper. How many water molecules you have? Of course, 6. Water is acting as a ligand. Water is acting as a ligand. Okay. So now you need to know if you have 5d orbitals. So what are they? So I would say that the three orbitals are between the axes and two orbitals are on the axis. What do you mean by this, on the axis and between the axes? So I mean to say, let me let me tell you some animation about that. Uh, yep, I'm going to share my screen. Okay, 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 okay. Can you see my screen?
Yes.
Y orbital, the xy lobe is oriented in between x and y axis. In the YZ orbital, the YZ lobe is oriented in between y and z axis. In the XZ orbital, the XZ lobe is oriented in between x and z axis. In the x square minus y square orbital, the x square minus y square lobe is oriented along the axis, along the x and y axis. In the z square orbital, the z square lobe is oriented along the z axis. So totally 5d orbitals are present. The d orbitals are the xy orbital, the yz
So
orbital,
इसमें
the xz
basically
orbital.
the purpose of telling you is that when we would be uh, studying the color of the complexes, so basically you must know how the ligands are going to make bond with the metal. So I want to tell you that when the ligands are going to approach the metal, so how they approach the metal. That's the main thing to discuss. How they approach the metal. So the ligands approach the metal on the axis. This is what I want to tell you, on the axis. Like I have written over there, when ligand approaches to the metal. So ligands is on the axis. Those orbitals which are on the axis, they will be repelling the ligand. They will be facing the ligand. So as a result, there will be energy difference between orbitals. As a result, there will be energy difference between the orbitals. So those which were on the axis, that was this and this, will be more repelled by the ligand. Of course, when they will be more repelled by the ligand, they will be having more energy. Therefore, therefore, energy would be higher after repulsion. Therefore, be energy would be higher after repulsion. Okay, energy would be higher after repulsion. That's the main key point. Like before the reaction, all the orbitals were at the same energy level. All the orbitals were at the same energy level, but when ligands approached to the metal, so basically the two orbitals would be having the higher energy and the three orbitals would be having the lower energy. So I can write in this manner. I can write in this manner. These are 5d orbitals which are at the same energy level, which are at the same energy level. Okay. So, but after approaching the metal, after approaching the metal, so then I can say energy difference is created. Energy difference is created. Two orbitals are at the higher energy level and 3 orbitals are at the lower energy level. Okay, and 2 orbitals are at the lower 3 orbitals are at the lower energy level. So the
So
enthalpy is created.
the
Sorry.
energy level depends on how far or how close the ligands are from each other,
Uh,
depending
Basically, it
on the
depends
axis.
upon which, like its strength of a ligand. If stronger ligands are going to approach the metal, stronger ligand, so means that the higher difference of energy would be created. So it would be absorbing more energy, more light, and then of course it would be giving you the darker color. It depends upon the strength of the ligand. It depends upon the how much there is a difference in energy between the two orbitals, between the two set of orbitals. This is called T2G. This is called EG, the set of two orbital, the set of three orbital. So how the difference is created? So of course, when the ligand is approached to the metal, so the difference is created. Now, what would happen? Like right now, if the difference is created, then what would happen? So I would say that when light strikes on the solution, let's whatever the solution you have right now, let's suppose we have copper sulfate that is of blue color. So uh, when the light strikes on the solution, okay, so electron absorbs an amount of energy. Electron absorbs, I'm talking about this electron. Electron absorbs an amount of energy, and it would excite to the higher energy level. And it would excite to the higher energy level. An electron jumps from the lower state to the higher state. Okay. So then the rest of the visible spectrum that is transmitted through the solution, we would observe that color. Basically, we observe complementary color. Basically, we observe complementary color. I'm talking. I mean to say, if copper sulfate is blue, means that copper sulfate is going to absorb visible light, and copper sulfate is going to absorb all the lights, but it is emitting only the blue color. So I would observe the blue color. I would observe the blue color. That's the key point. That's the main point. So we can see the complementary colors. I mean to say, red and cyan are complementary colors. Red and cyan are complementary colors. Sum of complementary colors is equal to white light. Sum of this and this would be equal to white light. Sum of this and this would be equal to white light. So when the complex is absorbing blue color, it would be emitting yellow color. We would see the yellow color. If someone is absorbing cyan color, it would be giving you red color. So you can see the red color complex. So this is very important to know that which color it has absorbed. You know, we have multiple frequencies. We have specific frequencies of a specific color. Like let's suppose if this complex is absorbing this frequency, so of course it would be transmitting some sort of frequency. So we would see the frequency value, and we would match that frequency value with the color. So we can determine that what is the color of the complex. I am talking about this. You can see this question. The complex ion is colored because it absorbs visible light. The absorption spectrum for the chromium is shown below. You can see this is maximum absorbance. Maximum absorbance. The color which is absorbed by the metal complex, you can't see that color. We can only see the color which is being emitted by the metal complex. So we will never see the absorbed color. The color which is going to have a lowest absorbance means the highest emission. That is this. That is this. Of course. So the frequency is this. The wavelength of the color is this. I can see the wavelength. It can be 550 or somehow that. So I would write that the violet color is absorbed because the frequency of violet color is this, and the frequency of yellow or green color is this. So violet color is absorbed and yellow or green color would be seen. Simple. Then You can see that the diagram shows the visible spectrum of a solution of vanadium. So maximum absorbance is 400. That the color is blue. Okay. So we can't see the blue color because it's going to absorb the blue color. And emission is this least absorbance, the minimum absorbance, that is green. So means green color, it's not going to absorb, it's going to emit the blue green color. So we can see the green color. So the color of the solution is green. Why? Because the minimum absorbance reflected back green color and blue color is absorbed. Are you getting my point? It's very easy. Yes or no?
Yeah. Yeah.
Yeah, good. Now the main point I'm going to focusing that why the S block elements are not colored. Then what would you say? Why the S block elements are not colored? Hmm? Hmm?
Because of the electron in the last orbital.
Basically, I'm talking about S and P block element. Sorry, S block elements in which you can see group one and group two, in which you can see group one and group two. So uh, let's suppose we have sodium. So sodium is 1s2, 2s2, 2p6, 3s1. You know, the energy gap is too much large to absorb visible light. They are not going to absorb visible light. They are not going to absorb. I told you this diagram in which you can see the delta H value. Let's suppose its value is 256 kilojoules. It would be absorbing that color, which is whose energy is equal to this. Like, I can't say that he is going to absorb every color. No, specific color it's going to absorb, which is going to match with this delta E value. If the color is not going to match this delta E value, so I can't say that it's going to absorb that much color. So same thing I'm going to say, energy gap for the group 1 and 2 is too much large. Of course, nothing value is going to match with that. So they are not going to absorb any of the color. That's why they are not colored. That's why they are not colored, of course. Okay. So you will see only the transition metal complexes are colored. And also the very important thing is that AgNH32. This is very important to know. AgNH32 plus. Okay. I am saying to you, this is colorless. I am saying to you, this is colorless. Now, why? Why this is colorless? Of course, this is silver plus one. Of course, this is silver plus one. So you need to write down the electronic configuration. So to make it shorter, its configuration would be this. Krypton is 36 and the proton number for silver is 47. Remaining one is 5s1 and 3d10. So after having plus one charge, it's going to lose one electron. It would become 5s0 and 3d9. Oh, sorry, 5s0 and 3d10. So 3d10 is full. So 3d10 is full. So means that if the 3d10 is full, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when the ligand approaches to this metal, so let's suppose division is going to take place just like that. 2 and 3. Electron, 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 electron. So how the excitation is going to take place? How? In that case, it was empty, like it had one electron only. It had one electron only. So the excitation has taken place between this and this. But what about in this case? All are full. Electron is not going to excite from the lower energy state to the higher energy state. I can't say that. I can't say that it's going to show the color. That's the reason silver complexes are white in color. Silver complexes are white in color. That's the main point. Are you getting this?
Yes.
Okay. Then basically we have uh, ligand substitution reaction. Then we have ligand substitution reaction. Ligand substitution reaction means that it's equal to the halogenation. If you remember when we were discussing group 7 elements, I'm talking about the periodic table, when we were discussing group 7 elements. So we used to say the more reactive halogen, the more reactive halogen is going to displace the less reactive halogen. The more reactive halogen is going to displace the less reactive halogen. Same goes with this. Same goes with this. The more reactive ligand, the more reactive ligand is going to attach, is going to displace the less reactive ligand. Okay, is going to displace the less reactive ligand. Now you need to know which is more reactive and which is less reactive. So this is called ligand substitution reaction. Ligand substitution reaction. Okay, so you can see that this is the copper complex, copper H2O6, that is of blue color, and I'm going to react this with the OH minus. Of course, I'm going to add sodium hydroxide in that. Okay, I'm going to add sodium hydroxide in that. So this is the structure for water. Water is acting as an acid. You know why? Water is going to donate its proton. Water is going to donate its proton basically. Okay, so you can see that you can see that here we have 6 water molecules and here we have 4 water molecules. So where are the two? Of course, the reaction has taken place between OH and then H2O. Okay. You will see a lot of example. You will see a lot of example just like that. Like where the ligand substitution is going to take place and where the neutralization is, where the neutralization reaction is going to take place. So you need to know this. Okay. And then he would be asking the color of the solution. You know, it's blue ppt. It's blue ppt, pale blue ppt. And then they are saying we are going to add excess sodium hydroxide. Then when you are going to add excess sodium hydroxide, so it would give you the deep blue solution. It would give you the deep blue solution. Then he would be asking to write down the formula. Then he would be asking to write down the formula. And then next thing he would be asking to add ammonia, few drops of ammonia into the complex. And then he would be asking, we are adding excess ammonia. Then what would be the color? Then what would be the type of reaction? Okay, what would be the type of reaction? So then he would be asking to add HCl, few drops. Okay, this is all about the copper complexes. Same goes with the cobalt complex. Same goes with the chromium complex. Same goes with the nickel complex. So that's the key point. That's the key point that we have to discuss. Okay.